Hello, in this video we're going to be looking at finding the derivative of a derivative or of a derivative again. Some notation things, if we know this prime thing to be derivative, but if we've got two ticks, we get our second derivative, which shows up here. You actually square the d, and then you square the x. Why that is, don't worry about it too much, but we'll eventually get there. So third derivative, we have a cubed on our d and a cubed on the x, and we do these three tick marks. After three, though, it's tough to read. So then you actually start writing the numbers, and this would be the nth derivative of a function. So in this example, I want to figure out what the second derivative of f of x is, and we know what the first derivative of f is. So all I need to do to find the second derivative is just find the derivative of this. If I was given the original function, I would find the derivative twice. So the derivative of this is going to be is f double prime of -3 will be the derivative of cosine is negative sine, pi -3. But then I'm going to need to chain rule that and find the derivative of inside of cosine because I've got that operation on the inside there. So that is going to be a pi. And then plus I've got to find the derivative of that x to the 4. That'll be 4 something cubed. And that something is a -3. And then we have the derivative of that constant on the end, which is 0. So this equals negative sine of -3 pi times pi plus, let's see, -4 times 27. That is going to be 108. And then the sine of -3 pi. Well, that is a coterminal angle. Ooh, do you remember coterminal angles? Sine of negative pi. So that is the same as the sine of pi, which is another coterminal angle of that. And so at that point, sine is 0. Oh, all that work just to get a 0? Ugh. So that is 0 plus 108. So f double prime of -3 is just 108. I don't even need to write that. F double prime of 3 equals 108. Huzzah! In this example, I want to write the equation of a line tangent to the graph at that point. So I need to figure out what is y prime going to be. Well, it's got this weird composition, so I don't quite know what's going on with that. But I do know how to find the derivative of a composition. I would use my chain rule. So I do the derivative of the outside times the inside, well, with the regular inside, multiplied by f prime of x. Okay, so, but then we want to find this at 0, so that'll be y prime equal, at 0, y prime of 0 is 2 times f of 0. They told me that up here. It's 3. Okay, so that's 3 multiplied by f prime of 3. All right, well, that's 6 times the cosine of 3 pi plus 81 plus 6. Cosine of 3 pi, that is going to be coterminal with just pi, and that's 1. Cosine of pi, no, -1, -1. So that equals -6 plus 81 plus 6. Which equals 81. So that is the slope of our tangent line for this function at 81. We want to figure out what it is at x equals 0. Oh, I should figure out the y value for that. So y is going to equal f of 0 squared. So y equals f of 0 squared. That'd be 3 squared. Still stealing that from up there. That's 9. So now we have a point. We have a slope. So we can put it into our point slope form. So y minus our y value, which is 9, equals our slope, 81, x minus 0. Colors got a little weird there, but whatever. There we go. There is the equation of our tangent line. Huzzah! In this example, I'm looking for the derivative of an inverse. So I've got my derivative of inverse set up right here. So that's telling me I want to do 1 over the value of the derivative evaluated at the inverse. So h of 3, since h is the inverse of f. So h prime of 3 is going to equal all this stuff. So what is h prime of 3 going to equal? Well, we know this. We know that if we put 0 into our function, we get out 3. So if we put 3 into our inverse, we should get back out the 0 that we initially put in. So h of 3 should be 0. So this equals 1 over f prime of 0. All right, so we just need to evaluate this thing at 0. So that is 1 over the cosine of 0 plus 0 to the 4th, which is 0, plus 6. So cosine of 0 is 1 plus 6 is 7. So h prime of 3 is 1/7. Huzzah! In this example, we're looking to use implicit differentiation to find dy over dx, as well as the second derivative of this function, which we'll also do implicitly. So let's start with dy over dx. So finding the derivative of that first bit, that's not too bad, it's just a power rule. So that's 2x plus the derivative of our second bit, which is going to be 2y, and then implicit differentiated is going to be dy over dx. And that's going to equal the derivative of that other side. Be very careful you find the derivative of that other side. It's very easy to just write a 1. Find the derivative of 1, 0. Now they're looking for what dy over dx is. They actually want us to tell us that. So we need to isolate that dy over dx. Well, that's just a little quick solve. So dy over dx is going to equal, we would subtract that 2x from both sides and then divide by that 2y that's right here with our dy over dx. So that is 2y. So our dy over dx, and I'll just write right here, is negative x over y. We found dy over dx. Now what we want to do is we want to use implicit differentiation again in order to figure out what the second derivative of this thing is going to be. So the way we've got it set up right now, this dy over dx equals negative x over y. If we find the derivative of that left-hand side, hey, guess what? That is our dy d squared y over dx squared. That is our second derivative. Sweet. Then we go to the other side. That other side is going to require some quotient rule because I have to do the derivative of the top, that's negative 1, times our bottom, which is y, minus the derivative of the bottom, which is a dy over dx, multiplied by the top, which is a negative x. So I'm just going to make this a plus, and then an x, over our bottom squared, which is y squared. Now, what I would like to do, since I've got that dy over dx in there, I would like to get that out. To get rid of that, to just have a more clean d second derivative, I'm going to plug this right in here because those mean the same thing. Dy over dx is negative x over y. So we can make our second derivative cleaner by plugging that thing in. Not in the simplification game, but this is just kind of making it look more proper. And most likely in a multiple choice question, they would do this. They wouldn't just leave it with that dy over dx in there. They'd make us simplify this down. So we could multiply that little bit together. And so we get d squared y over dx squared equals, we're going to get negative y plus, oh, no, minus x squared over y squared. I'm still thinking about ways that they could simplify this thing down. And I think I see something. So we could bring those fractions together and get a y squared, negative y squared, minus x squared. And then this would all be over a y. That's just the numerator. And then all over the old denominator, y squared. And so we got we got this. The reason I'm excited about that is where we started. We started up here that x squared plus y squared is 1, right? X squared plus y squared is 1. So when I'm looking at this, that is basically in that purple bit, that is x squared plus y squared. It's just negative. So that is just a negative 1. Ooh. So that is negative 1 over y squared. So that is just going to be negative 1 over y cubed. I could definitely see them being dirty and just writing d squared y over dx squared as that in a multiple choice option, and we would need to find that multiple choice option. So being able to simplify in those bits that we got earlier. So this, I think, is the simplest way. Again, we're not in the simplification game. If we're not simplifying, we don't have to. I would make sure that you do simplify in this bit. I have seen that being able to do that simplification as part of the scoring that will happen on an exam. That's it for our video on higher order derivatives. Mostly what you want to get out of this video is how you can be flexible with this idea of derivative, that it is not just a linear this one to this one to this one, and second derivative isn't always the second one down, and that you can mix and match in between these different pieces of derivatives to find other derivatives. Hopefully that made sense. Thanks for watching. Bye-bye.